He is professor of informatics in DMICE. He studied engineering and medicine at the University of Michigan. And after a decade of developing commercial software, including 7 years at Intel, he did a postdoctoral fellowship with us. So we're pleased to have him here. And upon the completion of his fellowship, he was recruited into DMICE as a faculty member. He has an MD from the University of Michigan and MS from our department. Dr. Cohen's research focuses on the application of data and text processing algorithms, natural language processing, especially machine learning techniques to biomedical data. Much of his work has applied text mining techniques to clinical and biomedical bibliographical text, with significant portions of work focused on problems in clinical informatics. He's had multiple R01s and private research grants for work in these areas, and he's published extensively on the application of advanced text processing techniques to biomedical and clinical research domains. His ongoing research programs include developing the ability for early detection of rare diseases using the EHR, extraction of structured data from clinical text to enable secondary research use cases, and improving usability and accessibility of EHR data for biomedical research. So he's going to speak first. One quick reminder before I forget, on the 21st, Nate Evans will be speaking at night at 11. So schedule slightly changes 2 weeks from now, and we won't have pizza there, so plan accordingly. And when you finish speaking, I will then introduce our second speaker, Adib. So, Dr. Cohen.
Thank you, Karen. So I'm going to talk about some work that we did over like the past year or so on detecting the rare disease AADC deficiency, aromatic L-amino acid decarboxylase deficiency. It's pretty rare. We have this work published in JAMIA in December, which was great. I will talk about the work that was published. It's, like I said, it was about a year's worth of work. But because this is a 2-for-1, I'm going to go kind of quickly and sort of lightly over certain aspects of this work. I'm happy to answer questions later after the 2-for-1 if people have questions. This may be the last paper I publish, or we publish, with traditional supervised machine learning techniques, and we'll talk about some of that at the end. So if you've heard some of this before, wait till the end. Okay, now we're not moving. Let's see if I can get the slides to advance. Oh, there we go. They were stuck. Okay, so there are lots of rare diseases. But there are so many, over 1,200, that they affect over 30 million people in the United States, which winds up being a pretty big amount of morbidity and mortality. So individually, rare diseases are pretty serious for individual people, but they're a significant health problem taken as a whole. You know, many of these rare diseases are often underdiagnosed. They're hard to diagnose. They have variable penetrance. Symptoms can overlap and be similar with much more common conditions. Physicians can be unfamiliar with them. We have a very siloed health system. So some physicians might see this part of the disease and others that part of the disease, and they might not be able to put it all together, and patients can remain undiagnosed for years. Now, it's not on the slide, but in combination with this, we have more and more advanced scientific approaches, genetic approaches, more and more new age pharmaceutical companies that are researching and discovering treatments for these rare diseases. So it's even more important that we identify these patients because there are treatments that can improve their quality of life. So the idea here is maybe in the 21st century, we're at the point where we can actually take a big picture view of this and not just, rely on individual interactions of patients with the health system, but take a whole health system view and look down at the data and identify the patients that maybe we need to take a closer look at to identify these rare diseases. Now, this particular work is really looking at AADC deficiency. Sorry, skipped over a slide. And I'm not going to go over this too much because we're limited amount of time here. But basically, this is a pathologic variant in the Decarboxylase gene. And this is an enzyme that's responsible for catalyzing the creation of neurotransmitters. So you can imagine all the neurologic and other symptoms that patients would have that can't correctly make neurotransmitters. So how can you detect an extremely rare disease on a large scale looking at EHR data? Well, the cohort of interest here was patients under 25 years of age. This is a disease of younger people, either children or teenagers or very young adults. We're not 100% sure of the penetrance, so we're not 100% sure about what patients who sort of have maybe a milder case might look like in their late teens or 20s. We had about 500 patients in the OHSU research data warehouse that met this criteria, and we had no confirmed AADC patients in that cohort. There was one that was suspected but not confirmed. So how do you study and detect a disease looking at the secondary uses of EHR data when you don't have any examples of this? Now, previously we did some work on acute intermittent porphyria where we had at least 30 positive cases that we could use. If you're used to the idea of supervised learning, part of that supervision is that you have some positive cases to supervise the training with, right? But you don't have that here. So what can you do? Well, one idea is that you try to recognize the constellation of symptoms and not look at the disease directly. So if you can enumerate what are the symptoms that are common with these patients, and then you can look for patients that have a constellation of these symptoms and don't have an explanatory diagnosis, another explanatory diagnosis, then maybe these are the patients that we should look at more closely and do a manual chart review and have their provider take a closer look at their case history. So when we look at symptoms, we can actually train machine learning algorithms to recognize symptoms, and then we can integrate this information together and make some kind of a ranking prediction of what patients are more likely to benefit from a screening test or at least a closer diagnostic review. Boy, it's not advancing. There we go. So again, I'm going to go over this quickly, but there's a whole list of symptoms that go along with AADC deficiency that are common in these patients: autonomic dysfunction, developmental delay, feeding issues, hypotonia, insomnia, mood disturbance. I'm not going to go over them all in detail, just that there's about a dozen of these that I think it's about 10 that perform a constellation of the symptoms that the patients get. So just to outline the methods that we used here, we have to annotate the data, chart data, from that patient population that we talked about for those concepts, which are the symptoms that you see. And then we're going to train sentence classifiers for those individual concepts. We're going to combine these individual sentence predictions into a single ranking prediction for the patient themselves to decide how likely they are to have these constellation of symptoms and maybe need a subsequent clinical review. And then we're going to manually evaluate the top ranking patients for the possibility that they may have ADC, for the idea that performing a screening test on them might be valuable. I'm going to skip over this, except to say that we had about 8,500 patients that had at least one pediatric neurology note, and we manually annotated any mention of any of those concepts with positive, negated, not about the patient, and hypothetical. Negated means that it says they don't have the symptom. Not about the patient means they talk about the symptom, but it's not specifically about the patient. It's like general medical knowledge. And hypothetical is like, well, we have to rule out that they have this symptom. That, you know, that the patient hypothetically could have that symptom. Of those 8,500 patients, we selected 10% for manual annotation. We divided the notes into sentences automatically using a Spacey tool. And then we assigned each sentence one of those concepts that were annotated. I should say that to make the annotation easier, we had the manual annotator annotate the whole text without dealing with individual sentences or something. They looked at each note, and then we broke the notes into sentences, and we looked for the overlap of the annotations with individual sentences. And we reduced then the annotations down from those 5 different categories just to 3 different categories: positive, negative, which means that the sentence didn't talk about it at all, and negative qualified, which basically means it wasn't about the patient, right? It mentioned the concept that it wasn't about the patient. That's one of the things you have to deal with when you're talking about classifying sentences that mention symptoms and stuff like that. It might mention the symptom but not be about the patient, and that's going to look different. That's going to be a different sort of class of sentences than a sentence that doesn't mention the symptom at all, and that's a important distinction. Typical thing that we divided into training, validation, and testing partitions. And then we had 90% of our data that we could use for that final evaluation of ranking all of those patients and doing a manual review of the top ranked patients and seeing how well the ranking algorithm did. I should point out that one of the things that you're probably not used to is this is a 3-way classification problem. This is not a binary classification problem. So a lot of your algorithms, you know, out of the box, they really kind of look at things as binary yes/no classification problems. But what we did was we actually did train supervised learning on this 3-way classification problem. We found that for this, it gave better performance. You could, and I'll talk about this a little later, combine these 2 negative classes together, but it didn't work as well. So the machine learning approach, we used the classic kind of machine learning approach with SVMs. We did, you know, cross-validation and parameter optimization. We tried some other algorithms besides SVMs, but the SVMs seemed to work the best. We had bigram, unigram features. We also used BERT encoding vectors as features, and that helped a lot. Really, the combination of the 2 of those was the best. Now, once we did that, we had individual sentence predictions, and each of those predictions was a probabilistic prediction about how confident essentially the algorithm was between 0 and 1 that it was correct. And what we needed to do, right, we need patient predictions, right? We need the predictions on how confident we are that the patient has the symptom, not that an individual sentence does. So we used something called a reduction function, a simple thing, not something that was trained, to collapse all the sentence predictions for an individual patient, all the sentences that corresponded to an individual patient, into a single prediction for the patient. And we used min and max and mean functions and NOR/ZOR functions, and we tested all of these for each symptom to decide which ones seemed to work the best for that symptom. And then we created an overall score for each patient, essentially by using our training data to train a Poisson regression model on each of the individual symptom predictions to predict how many symptoms that the patient actually has, as shown in the actual annotated gold standard that we had. So that's how we collapsed all the individual symptom predictions into a patient ranking score. And then we would take the top ranked patients and review them manually and see how we did, how many of those patients actually would benefit from a screening test and further clinical review. This is just the process. So we have results. The results are at the sentence level. How well did we predict the concepts according to the gold standard on sentences? At the patient level, same thing, but looking at the patient level of the data. And then at the disease level, which is basically looking at the whole population and how did we do with the patients that we rank the highest for the disease. So here's our sentence level concept classifiers. With AUC and average precision down there. Now I have to say some of these symptoms are very rare. They show up, I don't have a slide for this, but it's in the paper. They show up in, 10, 20, 30 sentences out of 8,000 patients times hundreds of sentences per patient. So when you see something like, an AUC of 68 and an average precision of 0.01, for autonomic dysfunction, that's actually not that bad at a sentence level, to be honest. It looks bad compared to what you're used to in terms of standard classification functions. But remember, each sentence is just one little piece of evidence that we have for a whole patient. And we're going to combine the evidence of each sentence in the patient to have a estimate for the patient itself. Now, some of these symptoms are relatively, easy. If you look at like epilepsy or seizure, the AUC is 0.94. And if you look at development delay, the AUC is 0.96. You don't get much better than that. Even have hypertonia, which is a very important symptom in this disease, the AUC is 0.94. So we have a combination of more common, easier to train and recognize symptoms and very rare symptoms that are harder to find, but we're able to at least do a lot better than random, right? So for an AUC, random would be 0.5, 0.68, and 0.74 for movement disorders. That's still better than random. So it's still better than not having a predictor for those symptoms. So that's just on the sentence level. When you look at the concept level, patient concept level evaluation, we've used those reduction functions to collapse, right, the predictions for each patient. Because what we really care about is, does this patient have this symptom or not? We don't care so much about, is each individual sentence prediction correct? And you can see that we have, essentially a lift greater than 1, which is the ratio of average precision in this case to the prevalence of that symptom in the data set. So each one of these is greater than 1, so it has some positive predictive value, you could say, all right, in this. And this is what the model fit looks like. This is our prediction of how many symptoms the patient had, and this is how many, this is how many, prediction of how many, and this is actually the count of how many of those different symptoms that they have. So it's not bad correlation. This is a D squared, which is sort of like an R squared for the Poisson regression function of 0.55. That's pretty respectable. So the big thing is the manual review, and I'm glossing over like how much work this manual review is and the manual annotation and all this. This literally took the majority of the time, both calendar and actual labor time. And it turns out that the ranking function is actually very good. If you look at the top 200 patients, we actually looked at the top 200 patients and the bottom ranked 200 patients. And you see that for the patients that were reviewed, and we decided that they required a clinical review of their case to decide if they needed a diagnostic test or further workup, there were no patients that met that criteria in the bottom 200. And of the top 200, there were 45 patients that were identified as needing further clinical review. So, this is a rare disease, one out of a million prevalence, one out of a couple million. It's very rare. We don't even know exactly. And so this is pretty good, right? About 25% of the cases that were top ranked reviewed, need further clinical attention. So for a rare disease that we have no disease-specific training data, this approach worked pretty well. The thing is that, you know, because it's symptom-based, there's nothing specific to AADC about this approach except a list of symptoms. So given another rare disease and a list of symptoms, you could do the same thing, right? In fact, some of those symptoms overlap with other rare diseases, so you could reuse those sentence classifiers and only create new classifiers for the additional symptoms that make sense for that particular rare disease. So, and that can be done with literature review and identifying, you know, what symptoms are known to correspond or, you know, or correlate somewhat with those particular rare diseases. As I said, most of the turnaround time, and this was about a year of work, but most of the calendar time was data annotation and manual case review, right? And like I said, there are, you know, over 1,200 rare diseases. If you were going to do each of them, we don't want to spend over 1,200 man years trying to identify all these rare diseases. So how do we get around this? So everything up till now is what's been published. Now I'm going off the chart, and this is what hasn't been published. So can we reduce this time? Can we use, you know, LLMs? That's the latest thing in, you know, that everybody's talking about. I'd rather say LLMs than AI. I think AI is a very broad term that could mean anything. Talking about large language models here. And the thing is that, you know, while people are promising LLM's going to do all kinds of things and become sentient and all that, I'm not dealing with any of that here. All I'm dealing with here is, can we use LLMs to do that extraction that we train this supervised machine learning on and save, you know, months and months and months of data annotation, right? So each of those machine learning algorithms was trained on, say, 80,000 samples, right? 80,000 manually annotated samples. Can we reduce that dramatically in some way? And I think we can. You still need some training data. Now, if you're going to use zero shot, which means no examples, or you're going to use n-shot learning, which means you have a few annotated examples that you include in the prompt that you feed to the LLM. So you need some training data because you need to know the right answer to feed into the LLM. And very important is that you need to be able to evaluate this. So you have to have some annotated data to evaluate and decide, you know, what approach is right, what prompt templates are right, how many, you know, n-shot examples works the best, what LLM that you have available to you is going to work the best. So you still need some annotated data. But I'm estimating that, you know, that a tenth to the fifth, 10 to 20% of the traditional amount of training data is what you could use when you're using LLMs. Because the thing is, the LLM has been trained on a huge amount of text, right? So it knows what English looks like, right? It knows synonyms, and it knows, you know, I'm going to say, I say knows like I'm anthropomorphizing it, but it has built into it some sort of mathematical relationship between the words and between similar meanings and stuff like that. When you're training with a standard supervised learning, even though we use BERT vectors, like I said, you know, you don't have that level, you're not starting on a base of that sort of level of sophisticated model of English. So when you're starting at a more sophisticated model of English, then what you need to teach it or give it in its prompt is how to tell it in a controlled way what you think is a positive and what you think is a negative, right? So I think that, so we've actually done some initial experiments with this, and I'll probably end on this slide after I explain it. But these are 5 of the symptoms that you saw that we did supervised classifiers in the prior work. And the SVM, which was trained on, you know, 80,000 sentences, is got the top performance. It's the first bar in each one of these symptoms. This one is developmental delay, feeding issues, hypotonia, mood disturbance, insomnia. But these other ones are variations of end-shot learning, where, you know, the end-shot learning is from 0 to maybe 8 annotated training samples. And you see that, you know, the results are competitive, especially because this was like 2 weeks of work, not a year of work, right? So if you factor in the reduced amount of training data and the relatively rapid development possibilities, it's looking very encouraging. Now, one thing I have to point out about this, and my colleague, Steve Bedrick, who worked on this with me, would have to say is that one of the negative things is look at all the variations of the different ways that you use end-shot learning. And there's no rhyme or reason about which end-shot learning approach is better than any other. So that needs future work. But overall, the results are competitive, and we didn't use a particularly medically trained model or something. We just used the generic Minstrel instruction model, which is a derivative of the Llama 2 model, and it just knows about general English. It doesn't necessarily know about any biomedical text or anything like that. So all of these things, there's lots of room for optimization. These are early results. It's just to show that we're already in the ballpark with not a lot of work. We can certainly make these better, and we will learn more in the future about the best way to optimize these. And I'm sure that we're going to approach the level of performance that we've been getting with traditional methods with a lot less work and a lot faster turnaround time. So we might be able to make recognizers for all of those 1,200 rare diseases relatively quickly using this instead of taking a year to annotate data for each one of the individual diseases. Okay, and I got 2 minutes left. Can I have time for one question?
I won't take the question. I'll leave that for next.
Go ahead.
Actually, I have a little bit of experience trying to tackle LLM or predictor model, classifier model to pick up multiple diseases based on genomic testing work for a genetic center. So they have tons and tons of whole genome sequencing data and what their diagnosis was, and just running NLP on their charts can pick up. But that said, my question is there any pre-formatting of the nodes that go into your training data set? I say that specifically example of like, sometimes the notes include, hey, here's a copy pasted excerpt about what this disease is from this paper, you know, and
so this is from EHR data, and it comes out of the RDW as is. And like I said earlier, maybe you didn't catch this because I kind of blew by it. We just used a spacey sentence parser and broke it up into sentences. So the sentences are fairly rough if you look at them. I mean, sometimes it does a really good job and sometimes it doesn't do such a good job, but we didn't change that. We didn't manually tweak that or do anything. We just fed each sentence into both the classification algorithm and the training algorithm and the LLMs just as it was. So we didn't do anything special or detailed about that. We didn't even annotate the sentences per se because it's kind of hard to do that. We actually annotated the paragraphs and then did essentially an alignment between the sentences and the paragraphs and decided if the alignment showed that the symptom annotation fell within the sentence or not, and then mark the sentence as positive or negative based on that alignment. So we really didn't do anything fancy with the text. It was totally meant to be, you know, kind of a reusable pipeline right from the EHR by way of the RDW and throw it through the automated chunking and pre-processing and classification as it was. So obviously you could do a lot fancier things.
I have a question. I mean, since what your algorithm is doing is predicting symptoms, could you not apply that to rare and not rare diseases? I mean, it seems like there's applicability.
You could. I mean, the idea is that, clinicians are good at recognizing
Yeah.
common conditions.
Right.
And so, they probably don't need as much help with that. And the rare disease population really could use more help and attention. And it's such a needle in a haystack problem that that's what a computer is good for, right? An automated method. So that's why we're focusing on this. But yeah, if there was a reason to want to identify at a large scale, at an institution or larger top-down scale, patients that had symptoms like hypotonia, for example, you could certainly use it for that.
Well, I mean, I'm even thinking about not things that are necessarily very rare, but even just less likely to occur.
Well, there's this whole other class of uncommon conditions with variable and sometimes surprising presentations, right? Like celiac disease, and Dr. Weiskopf and I are working on a similar proposal to do work in that area.
Great. Well, thank you, Dr. Cohen. Thank you for that. So it's my great pleasure to introduce our second speaker, Mohammad Adibuzzaman, also known as Adib. Thank you. Adib is an assistant professor in DMICE and director of the informatics program at the Oregon Clinical and Translational Research Institute that we all know as Oak Tree. Most recently, he was assistant professor of data and computing at Regenstrief Center of Healthcare Engineering, located at Purdue University in Indiana. He completed his PhD in computational sciences in Marquette, in Wisconsin, in 2015. His primary research interest is in health and healthcare data analysis using artificial intelligence techniques, specifically causal inference methods. His secondary research focus is on computing infrastructure for very large data sets in health sciences. In his role as director of informatics at Oak Tree, he leads the research data services team and provides campus-wide support for clinical data analysis for research. Adib's long-term goal is to create a data analysis engine with reproducibility, data governance, shareability, and I don't even know if shareability is a word, but it sounds good, and evidence generation in medicine. Welcome.
Thank you, Kat. It's a high bar after Aaron's talk. It was very technical, so I'll try. So thanks for the kind introduction, Karen. So today I'm going to talk about mostly about algorithmic bias, and some of the work that we have done is based on the summer R25 student that we had last year that Bill Hirsch is leading around a specific example. But let's start with what is algorithmic bias. So this is the outline that I have, and I'll focus like first half about talking a little bit non-technical, but more about the impacts and the ideas, like why we care about algorithmic bias and what does it mean, and how to address those issues. And then for the later half, or one section, I'll talk about a specific framework, which is a causal inference framework with a specific use case that Eva Truorti and Mohammad Adib, the student and the engineer that I worked with last summer. So what is algorithmic bias? So we know about algorithms is kind of impacting everything in our life right now. Here's a poster that says algorithms are like bacteria, but here you can make yogurt of it. So there are like good and bad things about algorithms. The question is how we use it. For today's conversation, I wanted to focus on data-driven algorithms. There are decision support systems that are more rule-based. That is not the scope for today's conversation. I'm focusing more on machine learning, AI-focused, data-driven decision-making systems. Now, what is algorithmic bias? Here is the definition. It's a acceptable definition. There are nuances to that. But in general, the idea is when an algorithm decision creates an unfair outcomes that unjustifiably and arbitrarily privilege certain groups over others. Now, there are a lot nuances here on all these words. How do you define what is justifiable and unjustifiable? It's not a technical problem, it's a philosophical question. How do you define certain groups? Is it race, ethnicity based, or is social status based, social economic status based? So the definition is a good start, but how do you interpret and implement that definition is based on different societal and philosophical values that we create as a society. Challenges with algorithmic bias. So there, like, how do you actually come up with the definition in the first place? That's the basic thing. And then there is, of course, lack of there's lack of quantification approaches. There is a higher level of complexity, and there is no standard framework for bias detection and mitigation. There are various ways people do this. There is lack of transparency in most of the machine learning algorithms, including large language models, lack of sensitive data on sensitive categories like race, ethnicity, and other things. And also, like, how unforeseen outcomes can happen based on algorithmic deployment. So those are not, you cannot predict everything before it is deployed. So you cannot proactively prevent everything before actually it happens. So those are like very high level issues, algorithmic bias. We are not going to talk about all of those today, but it is something we all need to think about when we are talking about algorithmic bias. So for the first few hub, as I mentioned, I'll focus on a few specific examples. All of those examples are very well known. Those are like some high profile publications. I have talked about some of those publications over various settings, but this particular one, this was a publication that was published in Science in 2019. And they were trying to see how this particular algorithm that Optum, which is an arm of United Healthcare, uses that for population health management at different providers at a scale. And it was shown for this study that if you look at this particular graph on the right-hand side, so the first graph, it shows the percentile of algorithmic risk score, that's the x-axis, and the y-axis you have number of chronic conditions based on race, basically black and white. So how does the algorithm works? So algorithm actually works basically giving a score based on the number of chronic conditions you have. And if you are at a top score, higher percentile, I think it was 98 percentile, like at the last vertical line that you can, I don't know if you can see this actually. So if you're above the 98 percentile, that means your chronic conditions or your score is pretty bad, you'll get more resources. That's how the health systems make decisions for resource allocation. Now, it was shown in this particular study that for African Americans or Black population, even though they had a similar number of chronic conditions, their score was lower for African Americans. And why this happened? The reason was basically to train the model to make this decision, they are using historical usage of clinical care. So their idea was based upon the fact that if you are more sick, you are likely to get more care, or otherwise, if you get more care, you are more sick. But that's a very strong assumption. Because of our societal structure, that's not the case all the time. You may not get care because of your other access issues and other things. And then they simulated that with a particular study, and this shows that if you address that particular bias, Black population, which received around 17.7% of the resources, the people that received 17.7%, that is the resources of the population that received the extra resources, that should be received by 46.5% of the Black population. So as you can see, that has a huge impact about how our healthcare provider system works. So this is just one example. Another example, and I'll talk more about this as a specific use case using the causal inference framework. But this particular algorithm was used in Florida for a for a justice system decision making, and the idea was they were predicting the likelihood of recidivism, which is the likelihood of re-offend based on some algorithmic process. And ProPublica, they did a particular study on this topic, and they found again the African Americans were risked higher compared to white Americans for the same history based on how the algorithm works and considers these different factors. And they showed some specific information on that. So this is another example just wanted to mention. And then algorithmic discrimination, also like large language model, we always have to talk about it, how these systems works. They inherently are based on how the data is fed into the system. So if the society, whatever bias we have in the data, that is also, of course, reflected in the algorithm, in the large language models. And I think you have noticed that in Google search right now, they have these generative AI search results. And so there are two types of search results they're showing. One is generative AI, and the other is just normal search results. Now, sometimes the generative AI results are hallucinating. They are just making the checks based on what they learn, because it's a purely correlation-based approach. But there are guardrails that they are trying to put in those generative AI models so that they can also be fact-based. They can also check the facts as well. But that is a big issue right now to focus. I'll talk about this one more example, and this is not a particular AI-based model, but this is more about how clinical workflow currently works. And this paper was published in New England Journal of Medicine a couple of years back as well, called Hidden in Plain Sight. And this is also pretty well known regarding algorithmic bias. And they showed various decision making, which is more rule-based, that is not the focus of current conversation. But I still wanted to bring attention to that topic that considers different age, race, and other factors to allocate resources or make clinical decisions. Now, there are controversy, or there are more awareness whether these models are actually should consider those factors, and is it the right thing to do? As an example, EGFR, the estimated glomerular filtration rate, that equation uses race as a factor. And if you're African American, you have more weight, or you have more EGFR based on the same creatinine level compared to the white Americans. It's like 20% more. Now, what it means is that you are considered more healthy because you have a higher EGFR based on your race compared to the Caucasian peers. Now, the hypothesis was that African Americans has more muscle mass, and that's a biological factor, and that's why you should consider that as a race, as a proxy for muscle mass. But there is controversy again, if it is universally true or not, and whether this evidence about 20% more EGFR is based on enough data and validated across. And so there are multiple studies that are happening. But this is just one example. There are many examples that have been highlighted in this particular study. And all of those, or many of those, needs to be analyzed and investigated further. So why this is happening? So those are like 4 examples I mentioned. And there are basically 4 reasons, or 4 buckets, like why this is happening. These are how the world works. That's on the left top corner. And the right top corner is how the data is being collected and analyzed. And the third piece is how the AI models are designed. And the last piece is how they are actually applied or deployed. So this is not only a technical problem. Again, this is how the world works, how the data is collected, how the model is being deployed, or there are statistical factors. That's the only technical piece. And then the deployment, like how do you actually monitor which application that you are using it for. As an example, for the first use case I mentioned, the model was working fine based on the purpose. But the question was whether can you use clinical care as a proxy for your sickness. That was the problem. So it's more about how you actually deploy the model. It's not about exactly the design of the model. So this is the same concept. So the main issue is problem is so if you are looking at this problem from a technical perspective or a data science or informatics perspective, the same four concepts, which is world, data, design, and deployment, can be formulated as problem specification, data collection and preprocessing, modeling and validation, and deployment. So for each of these steps, we have to be very mindful about how algorithmic bias can happen, and we have to be mindful about proactively monitor and prevent that. Now, what is the solution to address all of those problems? And of course, this is a huge, huge issue. There is no one single solution, but in general, we have to be technically very solid, like why we are applying this particular model and which database and those things. But it's more about technical solution. It's more about how there is a transparency. So the ProPublica algorithm or the United algorithms, none of those models are publicly available. The Google models, they're not publicly available. And there is a big controversy between Elon Musk and OpenAI, and it's kind of a similar idea. Like, are they publicly available? Can people validate and all those things? So transparency and monitoring, regulation is a key issue. There is a lot of conversations happening in the Capitol, the AI model, and these are like guidelines that are coming. They're not into our law yet, but people are thinking about it and asking those questions. So as a society, we have to come up with those decisions and regulations. And in terms of deploying as a specific model for a specific use case, we have to have diversity and inclusion and interdisciplinary collaboration so that everyone can provide their input. So here is a guideline from American Hospital Association to mitigate algorithmic bias. And they have these 4 steps. And again, it's not very technical, but as a health system, how can we prevent this bias? So it's kind of a checklist manifesto. So you kind of checklist all of those things. You can still have biases, but it's kind of a step forward. So first step as a provider or a large hospital like OHSU is how many algorithms are deployed in our decision taking. Do we know that? Do we have a list of all those things? Are we screening biases for each of these algorithms? If there is a bias detected, how can we retrain those models? And how can we prevent those? So those are like all policy level questions, but there needs to be certain protocols and processes in our hospital systems. Here is another guideline. It's kind of a questionnaire based. Like if you ask all these questions and answer those questions, the idea is you would be able to better understand what can happen with that particular algorithm. Like what will the automatic decision do? How will potential bias be detected? What are the incentives for the operators that are deploying those algorithms? How are the stakeholders being engaged? And how diversity being considered in the design and execution? So you see a common theme, like how do you actually address these biases from a governance perspective? And from a technical perspective, there are many different ways they define algorithms and processes for deep learning, generating AI. I'll talk a little bit more about causal inference framework, but that is something we can use to quantify different kinds of direct and indirect effects to quantify the biases that can happen. As an example, for gender-based admission, or race-based admission, how can we actually compute all these different ways that bias can be introduced? So I will talk about this particular use case using the causal inference framework that we have done so far. This is still pretty preliminary. We have done some initial work right now. We are trying to come up with a guideline on how to use this framework to detect biases. And we are actually writing a tutorial for EMEA on this topic if we get accepted on that. So the results are not fully validated yet. So before we dig into that details, I wanted to also talk a little bit about what those concepts of algorithmic bias means, algorithmic fairness means in terms of the societal issues that we address. Like inequality, equity, equality, and justice, those are the terms we use. Inequality is the idea that people have unequal access. Equity is the idea that how do you actually make sure that each group or each patient or each person needs what they have? So inequality more focuses on equal access, and equity focuses more on equal outcome. And justice, sorry, that's equity. And justice is more about addressing the underlying social structure so that that question of inequality or equity doesn't need to raise. So if there is an issue, how can we address that? Now, how does that translate into our machine learning AI models? So traditional machine learning algorithms, they focused on accuracy, precision, recall, sensitivity, specificity, on all those metrics. And most of the publications actually report that kind of numbers right now. But fairness criteria is different. You may have a very good high accuracy algorithm, but your model can be very biased. So those metrics needs to be standard in our publication processes and governance processes. So we need to report those concepts of equality in the model, which means do the model perform differently based on different demographic or ethnic groups or any other groups that we think can be disadvantaged. And how can we also avoid the biases in the first place? And those are the different concepts of health equity that should be introduced in our model evaluation process as a standard. There are few metrics that are being highlighted right now. So NCATS actually had a competition a couple of months back last year, and they actually looked into these particular metrics like differential validity and calibration fairness. And differential validity basically means if your model is performing across all the subpopulation the similar way. So how do you actually quantify that? Calibration fairness is another metric that kind of highlights on the predictive values, whether the true outcome is similar across multiple subpopulations. So those are the two metrics that we actually focused on Compass, and I'll talk about this a little bit more. So for this particular study, as I mentioned, they did this study with the recidivism database in Florida, and they collected all those variables that they could get this particular investigator, but they did not have access to the data or the variables. It was a black box algorithm to them, and they're trying to find out how this algorithm was introducing bias in decision making for justice system. I will skip this slide. I think I have mentioned this already. So one very basic test that they did was overall, if you look at all the Decide score, that is the score that the algorithm was predicting for each subgroup, which is in this case black and white, the score was pretty similar. Like you have same number of people for the black population across all the scoring, like 1, 2, 3, 4. It's kind of 300 people. Everyone is getting similar number of scores. So that's kind of weird. So that should not, usually it's like a normal distribution or a distribution more like on the right-hand side, which is you have most people scoring low, and then some people are high risk. So that's kind of a very basic test. So we used this causal inference theory to quantify some of the measures that we talked about, which is calibration bias, fairness, and all those things. Causal inference framework. I also just wanted to quickly talk about this. The idea was how to use this graph-based model to map randomized control trial from observational study. And that's the basic idea of the structured causal model framework that we use for causal inference. And as a simple example, you can think about like gender disparities in hiring. So in the decision-making process at the hiring side, there are multiple ways you can actually make the decision. What is your job qualification and some other protective attributes that can also influence your decision. We don't want the protective attributes to make our decisions. Like gender should not have a direct impact, but job qualification may depend on your gender based on our societal structure and what we have. But can we quantify that? Can we say how these decisions are made by what pathway? And that's the basic idea of transparent causal inference framework. So we computed all of those numbers: observational bias, bias in prediction, equalized opportunity, calibration bias, and causal bias with the standard fairness model. For this particular study, the data that ProPublica used, that data was available to us. So you used that data, and there are some results that I'm just showing highlight of that study quickly. So observational bias, in general, it was shown that African American population was, their decile score, the predictive score, was 43.7% higher on an average, with a very high p-value. Then also in the prediction process, African Americans were assigned a higher score, then they actually reoffended, 14.4% more higher score than they actually reoffended. So the actual truth versus the prediction is 14.4% versus the Caucasian group was 11.6% lower than actually what happened. Equalized opportunity, which is the likelihood of being assigned a positive outcomes across multiple subpopulations. For that metric, African Americans were 30.5% higher than the mean score compared to the Caucasian group. And there may be reasons to that. We need to explore that, but those are the numbers that we found from that study. One thing that we found also was the actual reoffense rate between these two groups was 6.5% higher for African Americans versus their Caucasian peer or white Americans. But there may be underlying reasons for that, and that's kind of their socioeconomic status or their access to education or something else. So those factors are not considered in the model. So that goes back to the question of our societal issues of equality, equity, and justice. So it's not a race-based things, but those factors are not considered in the model. So the question is, can we come up with a model where we can simulate or predict if we intervened with those other factors in the society, things would improve or things will have a better outcome in the algorithmic process. And that's the standard fairness model that has been proposed by Dr. Barenboim and his students in Columbia University. So I actually worked with him at Purdue University for a while, but we still have some collaboration on that. But this is the framework that is being developed by this theoretician from Columbia. And I'm trying to use it in applications in algorithmic bias. So we also computed all of those numbers based on this standard fairness model. And we showed like how much of that bias is coming from direct effect, indirect effect through race versus what is actually should happen. So if you look at this particular diagram, the total variation between predicted and true outcome is shown on the rightmost histogram or the rightmost bar, but that is happening because of some indirect effect as well. So direct effect, so DE is counterfactual indirect effect and direct effect and counterfactual indirect effect. So we should not consider those spurious associations or these indirect effects. So we should only consider that is the direct effect and that's the bias piece. And somehow we have to mitigate that bias. But can we still quantify this? And then we can come up with models on how to intervene to prevent that. So that's the framework that we're trying to build right now. So this whole work right now is to just show that this model can be used as a standard solution to quantify bias in algorithmic decisions if you have a graph-based model, and then you can come up approaches on how to mitigate that. So in summary, just the last piece highlighting that, we have shown that this model might work for predicting and quantifying biases, the causal inference framework, but the challenge is much bigger. The algorithmic bias challenge is much bigger, which is require a systematic societal and multidisciplinary collaboration, governance, regulations, and awareness. And the key is governance and human factors. So I'll stop there and take any questions. Yes.
Over time, both our speakers might be available for a few minutes after the session. So this is great. I'm glad the two of you spoke the same day because I learned tons. One of the things I guess I was listening to a podcast about the bias in the data set that the algorithms are used. So I assume that you're also looking at the data. Or
I am not looking at this particular use case, but that's an active area, like why the data is biased in the first place. Actually, Nicole does a lot of work on that.
and then two quick announcements, actually three quick announcements. Next week is a virtual session. Dr. Hirsch will be introducing our speaker, Graham Grieve, on a pioneer.
The inventor of fire.
Pioneer for fire, and he's speaking from Melbourne.
Yeah, Australia.
Yeah, so we have that speaker next week, and then in 2 weeks, as I mentioned earlier, our speaker is Nate Evans, and he will be speaking at the night at 11 o'clock. So next two sessions, we won't be here, but please join us, and thanks, everybody. And if you haven't signed in, please do sign in. That sign in helps us know how much pizza to order.